Geometrical thinking in the 20th century has been revolutionized by the advent of a branch of mathematics called topology. This is a distinctly 20th century development. Of course, everything is a continuous evolution, and the branch of mathematics which I'm calling topology has evolved out of the past. And I would like to show you some of the points of contact with past developments. Before beginning, however, I'd like to describe in a word what topology is. Topology is the study of geometry without regard to size or shape. Now, that sounds like a mind-boggling concept. What can you possibly say that has any geometrical truth without regard to size or shape? Well, I'm going to show you a couple of examples. Back in Euclid's day, way before Christ, he wrote a textbook which served as the textbook for geometry for 2,000 years. And in this textbook, he started with the 5 postulates that I described at the very beginning of the series of programs and proved everything from those 5 postulates. And one of the things he proved is a rather remarkable theorem, and that is that there are only 5 regular solids. And I have them here in front of me. A regular solid is a solid which has flat faces, and the faces are all congruent polygons. Now in this case we have what's called a tetrahedron. A tetrahedron has triangular faces. There's 4 of them, and it's the answer to a nice little parlor puzzle, and that is, how can you make 4 equilateral triangles out of 6 matches? That's how you do it. This, of course, is the well-known cube, and I've put these braces in here because if I didn't have them in, it would be completely wobbly. The triangle is the strongest shape, and this is why, for example, guy wires are used on towers. But this is a cube. This is called an octahedron. It has triangular faces, and it has a square middle. This is called an icosahedron, and it has triangular faces, lots of them, as you can see. And this one here in front of me, which I'm not going to pick up, well, if I pick it up, it'll come apart. It's called a dodecahedron. And as you can see, I've made it out of little pentangles, pentagons, that fit together like this. These are the only 5 regular solids that can possibly exist. Now, there's an interesting fact about these solids, which can be generalized to many other shapes. And that is, if you count the number of faces, those are the flat areas, and then count the number of edges, and then count the number of vertices, which are the points, you have 3 numbers. Now do the following thing. Take the number of faces, subtract the number of edges, and add the number of vertices, and you always get 2. Now, it doesn't matter what shape you have. Incidentally, I'd like to talk in terms of topology. The fact that these are flat is irrelevant. Imagine them made out of rubber, and imagine I could just put my mouth to it and blow them and plump them up into a round balloon. They would then look like maps on a surface with curved edges. The same theorem would be true. In other words, the number of faces minus the number of edges plus the number of vertices is equal to 2. It turns out that this result is true not only for these solids, but it's true for any map that you could possibly draw on the surface of a sphere. If you draw any map, and count the number of edges, and the number of faces, and the number of vertices, make that combination, you will always get 2. Over here, I have an example of one very simple map right in front of me. It's simply a triangle and a bottom part. And if you look at this particular map, it's not regular at all. But how many faces do I have? I've got the triangular face, the bottom face, and the rest of the top. There are 3 faces. There are 4 edges. I've got this one, this one, this one, and the one that goes around the back. And I've got 3 vertices, 1, 2, 3, and this combination is always equal to 2. Now that is a theorem of topology. This is true no matter what the shape of the sphere actually is. Now, suppose I took this sphere and stretched it, made it a great big long thing, and then suppose I gave it various bumps and ripples in it. The theorem would still be true. It doesn't matter what the size of the sphere is. It doesn't matter what the shape of the sphere is. All that matters is drawing a map and counting these three quantities and making the calculation. Now, I'm not going to go into how you prove these things, but it's very interesting. Incidentally, in a little historical footnote, I might mention that back in the Renaissance days, when Kepler was trying to decide the distances between the planets, he thought that perhaps there was a connection between these so-called Platonic solids, these 5 regular solids, and the distances between the only 6 planets that were known at the time. 6 planets make 5 gaps. And so he figured that maybe they were nested between each other according to this particular scheme, where you have the 5 solids fitting into the concentric orbits. Of course, he was wrong. These things don't always work out. You remember in the program on the last program where I was talking about higher dimensions, I mentioned the principle of duality. And the principle of duality says that any time you can say something that is true in 3 dimensions, it will remain true if you interchange the word point and the word plane. In other words, if you change the word point and the word plane, you'll still have a true statement. That can be illustrated also by means of these solids here. If I take, for example, this little tetrahedron, in the middle of each plane face, imagine a point right in the middle of each face. What I've done is I've reduced the planes to points. Now join up those points, and what you get is another regular solid. You can do that with each one of these regular solids. This is called the principle of duality for the regular solids. And there's a little graphic which illustrates this. You will see that when you take the tetrahedron and take a midpoint in each of the faces and join them up, you get another tetrahedron. This is expressed by saying the tetrahedron is its own dual. If you do this with a cube, you end up with an octahedron inside the cube. And incidentally, if you start with the octahedron and did this trick, you'd end up with a cube. When you take the dual of the dual, you're back where you started. And the last diagram on the bottom, which I care not to describe, shows the relationship between the 2 remaining solids, Platonic solids. So the principle of duality is well illustrated by this little device. Now, let's consider another topological theorem. This topological theorem, which I now wish to describe, is called the Jordan curve theorem. And it has to do with the following property, which is true on the sphere, and anything that's like a sphere, no matter how you deform it. That is, if you draw a curve that closes upon itself, it divides the sphere into 2 pieces, an inside and an outside. Now, doesn't that sound simple? Really simple. However, if you look at some curves, and I have some curves here that are pretty weird, you will find that in practice it's often difficult to describe whether a point is on the inside or the outside. Here we have a simple closed curve. Now, it may not look very simple to you, but what simple means is simply that it doesn't cross itself, and it finally ends up joining up, so that wherever it started, it joins up again. That's a simple closed curve. Question, is point A inside or outside? Is point B inside or outside? It's not terribly easy to tell. If, on the other hand, you're able to color the simple closed curve, I have one in front of me here that's colored. And because of the colors, it's much easier to tell whether something is inside or outside. If it's in the colored area, then it's inside. If it's not in the colored area, it's outside. So you may have points that look inside, but are really outside. Now, there's another little trick that's rather cute, and that's the following. Suppose you have 2 points in the same curve. I don't know if you can see that very clearly, but if you take a look at one of these simple closed curves and 2 points, the question might arise, is it possible to go from one point to the other point following the curve, following the maze, if you like? There's a nice way of doing it, and that is to join the 2 points, count the number of crossings, and if the number of crossings is odd, then they're on opposite sides of the curve. Why is this? Because every time you cross the curve, you pass from inside to outside, and then from outside back to inside, and then from inside back to outside. And if there's an odd number of crossings, you end up on the other side. So in both of these cases, it's not possible to go from one point to the other point because there's an odd number of crossings. That is called the Jordan curve theorem. Once again, you would say to yourself immediately, I think, well, it sounds obvious that a simple closed curve should divide a surface into 2 regions. In fact, it should be true not only for a sphere, but for any surface, right? Wrong. It's not true for every surface. There are many surfaces for which the Jordan curve theorem does not hold. I have such a surface in front of me. This curious looking thing, which many of you have probably seen, is called a Mobius strip. It's a little toy, and the way it's formed is by taking a piece of paper, a rectangular piece of paper, giving one end a half twist and then bending it around and joining it up like this. Now what I've done is I've drawn a curve around the middle. You see that curve around there? If this curve divides the surface into two pieces, then when I cut it, it should fall into two pieces. Let's see what happens. I'm just going to cut around here and find out what two pieces I get. Incidentally, this is also a dandy trick. If you want to win a few wagers, you've got to find somebody who hasn't seen a Mobius strip before. But you can get almost to the last point and hold it up like this and say, okay, now I'm just going to complete this last cut. What's going to happen? And people who look at it would almost swear it's going to fall into two pieces. But when you finish the cut, it's one piece. And this shows that that particular curve, that Jordan curve, does not cut the surface into two pieces. Fascinating. Now, I started, in that particular case, with a Mobius strip, just like this one. You see this? Now, Mobius strips are weird things, because you might say there's two sides to the Mobius strip, right? Okay, give a Mobius strip to your little 6-year-old son or daughter, and ask them to color the two sides, one side red, the other side green. They'll get frustrated very fast, because as soon as you try and color this side red, you follow it around, you color, 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 you find out the other side's got to be red too, because really, there's only one side. There's not two sides. It's a one-sided surface. Similarly, it's got two edges, right? No, it doesn't have two edges. It's only got one edge. If you follow this edge around, you end up on this edge. So this is a surface with only one side and only one edge. This is not topologically equivalent to a sphere. So the question is, how do you tell the difference between things when you're not using size or shape as a way of telling the difference? I cannot resist one further trick. The further trick is this. If you take a Mobius strip and instead of cutting around the middle, suppose you cut only a third of the way from one edge. Shouldn't make any difference, right? You just cut around a third of the way from one edge. Well, I've got a Mobius strip here, and I started cutting, before the program, a third of the way from the edge. You see that? I'm just going to continue the cut. And you try and figure out what's going to happen when I complete this cut. Yeah, there we go. Notice, it's very interesting. Because of the fact that the two edges are really the same edge, I've got to go around twice. Because by the time I get back to where I'm started, I'm on the other edge. I'm 1/3 of the way from the other edge. So I must cut around twice. And when I cut around twice, I have this. Very interesting. In other words, if I go a third of the way around, it is a Jordan curve again. It matches up. It's a simple closed curve, but it cuts the surface into two pieces. So what we found is that on a Mobius strip, the Jordan curve theorem doesn't hold, but sometimes it's true and sometimes it's not true. It depends on the curve. Incidentally, there are many other surfaces which exhibit a similar property, and I could have been less bizarre about it. Let me just show you one such surface. I have to reach back here. This surface, which you would probably call a, well, it looks like an inner tube or a donut. The mathematical name for it is a torus. And I've drawn a couple of curves on it. One is around here. That's a Jordan curve. But you see, that doesn't cut the surface into two pieces. Once again, I've got a Jordan curve which goes around here. That doesn't cut the surface into two pieces. But if I drew a little circle here, that would cut it into two pieces. So the Jordan curve theorem says something significant about what's called the topology of this particular creature. Now, I would like to describe a very nifty gimmick for talking about things like Mobius strips and things which are much fancier, in fact. And this is called, it's a gimmick which is trying to represent everything by means of flat figures. Now, I've got some drawings here in front of me which are just rectangles. I'm going to show you how it works. If I take an ordinary rectangle like this and make an agreement that all the points along this side in that direction are going to become identified with the points along this side in the opposite direction. Now, what do I mean by identified? Well, what I mean is that this is a funny kind of a trick, but suppose you were an ant crawling along the surface. As soon as you come to this point, you're magically transported to this point, and you continue coming in the same direction you were moving before. If you then sort of take a different path and come along to this point, you're magically transported to here. In other words, you cannot escape from this rectangle by going out either of the ends. As soon as you go out one of the ends, you come in the other end. This is actually a Mobius strip. Because you see, if I just took this rectangle, cut it out with scissors, turned this side half a turn, and then joined it around, that would be a Mobius strip. So this is simply another way of describing a Mobius strip. The advantage is that it's flat and it's more understandable. Let's try something different. Suppose I join this side with this side in the same direction. What would I have then? In that case, I have to bend it around and join them up directly, and I have what's called a cylinder. Suppose I then identify this side with this side in the same direction. Now, can your imagination stretch that far? First, you fold it around to make a cylinder. Then you take the two ends of the cylinder and bend them around to make a torus. So here I have a torus, and here I have a Mobius strip. And this is a very handy way of describing these surfaces. Now you notice, if I draw a line right down the middle of the Mobius strip, that's like cutting it down the middle. That doesn't divide the Mobius strip into two pieces. How come? Because these points up here are connected with these points down here. They're connected by means of this agreement that they've been identified. Similarly, if I cut the torus this way or this way, it doesn't cut it into two pieces. Let's try a few other tricks. Suppose I do this. Suppose I identify this side with this side. That gives me a cylinder. Now I identify this side with this side in the opposite direction. Whew. That's kind of hard to imagine. First of all, I have to bend this around to make a cylinder. Then I have to somehow bring the neck around, but I can't join it onto the bottom directly. If I join it onto the bottom directly, they're not going to be opposite. You see, these have to be opposite to each other. They must be opposite to each other. So how do I do it? What I do is I bring it around, and I have to sort of stick it through the inside and join it down this way. And this gives me a surface which is called a Klein bottle. I believe I have a drawing of a Klein bottle there. There's a Klein bottle. Now that's a strange surface because in fact you see it must intersect itself in 3 dimensions. However, in 4 dimensions, as I explained last time, it does not have to intersect itself. What you do is you wait until the neck is just getting up to the point of intersection, then you slip into the 4th dimension, shove it inside, slip back into the 3rd dimension, and join it up. And this way, in 4 dimensions, you can realize this surface without any self-intersections. Now, these various surfaces are great toys. I'm going to deal with just one more. Suppose I take a rectangle and identify these sides in the opposite direction, and I also identify these sides in the opposite direction. Whew. What do I get then? Well, this is, believe it or not, the projective plane. Remember when I was talking about projective geometry and the line at infinity and so on? Well, this, in fact, is a way of describing the projective plane. And I'd like to just enlarge upon that a little. You may remember that the projective plane could be represented by means of a sphere. And I'll have this drawing, which I used earlier in the last program, the projective sphere. And the projective sphere is obtained, as you recall, by using great circles, and you must, in this case, on the sphere, you must identify the opposite points of the diameters. In other words, just like on the rectangles, being at this point on the diameter is really the same as being at this point. If you're at this point up here, you can magically transport yourself down there in 0 time, because they're really the same point. These points are identified. Now, what can I do with the projective sphere? Well, what I can do, first of all, is throw away the bottom hemisphere and only deal with the top hemisphere, because the bottom hemisphere has points which are duplicated on top. The only thing I can't get rid of is the fact that around the boundary, you have a whole bunch of diameters around the boundary where these oppositely oriented points must be identified. Well, if I flatten this down, what I get is an ordinary disk. This is a disk. You see what I've done is I've just taken this and flattened it down. And what I have is every point around the circumference of this disk is identified with every other point around the circumference on the opposite side. So for example, if I were an ant crawling along this surface and I got to this point, I would magically be transported to this point and would continue my journey. This is the projective plane. And if you think about it a little bit, I think you'll realize that if you just square it out a bit, it's really the same as the rectangle that I showed you a minute ago, with these two sides identified in the opposite direction and these two sides identified in the opposite direction. It's simply saying that points opposite to each other all around the circle are identified. It's another way of representing the projective plane. Incidentally, one rather amusing consequence of this is that if you were to cut a hole in the projective plane, you would have a Mobius strip, which shows that the projective plane also has only one side. It's not a two-sided surface. It has only one side. Now, all of this sounds very, I suppose, impractical. The fact of the matter is that topology is an extraordinarily practical subject. It's absolutely astonishing how important it has become in the 20th century. What I have been showing you here is just little parlor games that are sort of the ABCs of topology. But once you progress further, you discover that there are absolutely fantastic theorems which can be proved. I'll give you one example. As a matter of fact, I'll give you a couple of examples. One example which is quite famous is called the fixed point theorem of Brouwer, a mathematician named Brouwer. What this basically says, I'll translate it into ordinary everyday language. Take a map of Montreal and take another map of Montreal. It doesn't matter if they're on the same scale. It doesn't matter if they're even accurate maps. The only thing that matters is that there are geographical correspondences between them. Okay? Put the one map down on the floor, take the other map and crunkle it up without ripping it. Just crunkle it up into a ball and drop it on top of the map that's on the floor. What Brouwer's fixed point theorem says is that there must be one geographical location on the two maps where they are directly above one another, exactly vertically one above the other. And that's called the fixed point theorem. Now that may sound like a rather useless result. It is not useless at all. It is an extremely useful and practical result. Basically what it says is that any continuous mapping of a disk or a rectangle into itself must have a fixed point. And that is probably the first really, really significant theorem in topology. And from that theorem, many others followed. One theorem which followed, for example, is that, and again, these sound silly, but they have many applications in engineering and so on. If you had a billiard ball that had hair growing on it, one of the theorems of topology says you can't comb it without getting a singularity somewhere. Now, if you've ever noticed the back of a boy's head who's got, you know, a standard boyish haircut, there's always a little whorl at the back of the head. That's the theorem in topology, which says you can't comb it entirely neatly. There's got to be one point which is called a singularity, at least one point. Now, that is precisely the thinking that led Einstein to conclude that there must exist black holes in the universe. Now, I'm stretching it a bit. But the same kind of thinking applied to the four-dimensional space-time manifold that Einstein was talking about in his theory of relativity led him to the conclusion that there must be a singularity somewhere in the universe. And this singularity is what is called a black hole. And there are many interesting books on the subject. They're fascinating things. They're not stars. They are like cosmic vacuum cleaners. They suck in everything that comes in its vicinity, and where does it go? Maybe into another dimension? Perhaps it emerges on the other side in some other universe that we can't even perceive because it's in another dimension. Nobody really knows, but these black holes, astronomers believe that they have now detected 1 or 2 black holes in the universe. I would like to give a more mundane, down-to-earth example of how topology is influencing modern thinking. There is a brilliant French mathematician named René Thom, T-H-O-M, who rather recently, within the last 15 years, became interested in anthropology. And one day, as he was looking through an anthropology book, he noticed the skulls of chimpanzees and apes and Cro-Magnon man and Neanderthal man. And he noticed that they all look like topological transformations. That means they all look like continuous deformations of each other. And this really fascinated him, and he ended up writing a book called Catastrophe Theory, which is the study of evolutionary processes using topology as the main mathematical tool. The interesting thing about this is it is a non-quantitative type of mathematics. It tries to describe qualitatively what happens without being precisely quantitative about it. And this theory of catastrophe theory has been applied with, it's not clear yet how useful it's going to be, but has been applied to such things as embryology, the development of an embryo in the womb. It has been applied to animal behavior, how an animal, for example, a dog who is intimidated will first cower and then at a certain point will lunge and attack, and how to describe this mathematically, how to describe the evolution of a language, how to describe the learning process, in fact, how to describe any evolutionary process. This is the task that René Thom has set himself, and I hope that this very brief insight into the evolution of geometrical thought will stimulate you into realizing that mathematics is indeed a rich cultural heritage that deserves much greater exploration by people who need not be intimidated by the kind of formalism and the abstract notation that often shrouds the subject. Thank you.